In this video, I want to talk about Maxwell-Boltzmann distribution and kinetics, and then I also want to talk about the first two types of reaction rates and how we work with those. So first of all, when we see this here, Maxwell-Boltzmann is the distribution in which we can look at temperature or we can look at mass. Now we had this in thermochem, so just a quick review, we have number of molecules on the left-hand side on our y-axis. On our x-axis, we have kinetic energy. Now if these products, if A and B were both the same molecules, then what we would do is we would compare their kinetic energies. And so if we look at the kinetic energy of B, that lies on the x-axis right here. A's kinetic energy lies on the x-axis there. And where I'm looking at is I'm just looking where that peak falls on the x-axis, where this peak falls on the x-axis. We're not looking at heights of peaks or anything like that. We're technically looking at area under the curve. So if I compare B to A, B has a greater temperature than A. Now, how does that correlate with kinetics? Well, what we could do is we can say, all right, we have a threshold here of the energy that must be overcome to reach our activation energy. And that's what we saw in our little graph where we had this here. This would be our activation energy from there to there, our reactance to our peak, our transition state. Well, this would be like the amount of energy that must be put in to overcome the activation energy. Now, if we look at A, these molecules to the right of this activation energy have sufficient energy to be able to overcome activation energy. So that means that these molecules to the right of this line could have an effective collision. That doesn't look like a very large number compared to all this space over here. And so since A is at a lower temperature, there's not very many particles that have sufficient energy to overcome the activation energy. But let's look at B. B is a higher temperature. So all of these particles to the right of this line, you see it's a lot greater than the particles for A. Those particles have sufficient energy to overcome the activation energy. So this is just another way to relate Maxwell-Boltzmann distribution to temperature and how it affects the rate of a reaction, because now I have more molecules that can overcome that activation energy. So that is the deal with Maxwell-Boltzmann. Now, specifically, because this temperature change has such a large shift on those molecules, we say that the reaction rate doubles for each 10 degrees Celsius rise in temperature. So what you should have in those lines is that the reaction rate doubles for each 10 degrees Celsius rise in the temperature. The next thing that I want to talk about is different types of reaction rates. So this first type of reaction rate that we're going to talk about is instantaneous. Now, before we get into that, we need to talk a little bit about rates and what that means, what it's measured in, and all that good stuff. So I want to scroll down a little bit. So when we're discussing rate is a change in concentration over a change in time. So what we have going on is our concentration of our reactants as well as the concentration of our products are changing over time. And is due to how fast or the likelihood of having those effective collisions. Now, what do we notice about our reactants? What happens to the concentration of reactants over time? Well, those reactants are being used up, right? Well, since those reactants are being used up, they have negative rates. Their concentration is decreasing over time. My products, on the other hand, I'm making those products. I'm producing those products. So products have positive rates. They're being made. Their concentration is increasing over time. So this negative and positive sign is very important. If we're working with rates on reactants, those rates are negative because we're decreasing concentration over time. If we're working with products, we're going to have positive rates because we're increasing that concentration over time. Now, what units do we use for rate? Well, since rate is concentration over time, our units is going to be molarity over whatever time unit you're working with. This time unit can be seconds, it can be minutes, it can be hours, it can even be days or years, depending on what time unit you're working with. So our units for rate is molarity over whatever time unit you're working with. So now let's talk about instantaneous rate and what that means. An instantaneous rate means a rate at a certain amount of time. So let's say I was looking up here, and the graph that I see here is a concentration versus time graph. So we have a concentration decreasing over time, so that's NO2. We have two concentrations increasing over time, NO and O2. Before we get into what instantaneous rate is and figuring that out, I want to kind of do a little side note here. Can I figure out which one of these are my reactants and products based upon this graph? Well, the answer is yes, I can. If I look at concentration over time, and I know that a concentration is decreasing, that's going back to what we were saying down here. Reactants decrease their concentration over time. So what that means is that NO2 right here is my reactant. So I can write a reaction based upon this graph. So NO2 is my sole reactant here. I actually have two products here. And how I know that NO and O2 are my products is because those are both increasing in concentration over time. So I'm going to write NO plus O2. Now, this reaction is not balanced, so we need to make sure that we balance that. And in order to balance this reaction, we need a 2 there, and we also need a 2 here, and that's balance. Now, there's another thing I want to point out here. Notice how the curve for O2 and the curve for NO are not the same. So what is that telling me? That means that NO's concentration is increasing at a faster rate than O2's concentration. Why might that be the case? Well, the reason why is because of these coefficients here. What do we notice about the relationship between NO and O2? We have a 2-to-1 relationship. So what that means is that when two NO2s collide, making effective collisions here, right? When two NO2s collide, effectively, we're producing 2 NOs and only 1 O2. So because of these coefficients, that's why I have twice as much NO produced as I have O2. So coefficients, stoichiometry, I promise you, you're never going to get rid of stoichiometry, so embrace it, okay? Learn to look at relationships, and it'll make it so much easier for you there. All right, so now we have NO. We know that's a product. We know it's twice as much because it's a 2 coefficient. We have O2, which is another product. They're both increasing in concentration over time. And then we have 2 NO2. And you see how it's a pretty steep curve? That's because 2 NO2s are decreasing over time. So we have that as our reactant there. Now, going back to instantaneous reaction rate. Let's say we had time of, let's put this in red. We had a time of 100 seconds on this little graph here. And I want to know the exact rate of NO2 at 100 seconds. Or I want to know the exact rate of O2 at 100 seconds. Or even I want to know the exact rate of NO at 100 seconds. What do I do? How do I find my instantaneous reaction rate? Well, because these are curves, remember we know that rate is your change in concentration over the change in time. You might think, well, I know concentration and time's here. Why don't I take the slope? Well, can you take the slope of a curve? No. But what you can do is I can draw a line tangent to that curve. And if I draw a line tangent to that curve, I then can take the slope of that line. And the slope of that line would be change in concentration over change in time. So let's just look at NO2. And we want to take the instantaneous rate of NO2 at 100 seconds. So we are going to draw a straight line tangent to that curve. I'm going to try my best to draw a straight line. Remember that a line tangent to the curve only touches the curve once, and it only touches it at that particular time in this case. So it's only going to touch it once. That should be the closest that I can technically draw to a line tangent to that curve. So that is your first thing to do when you're looking for instantaneous rate. You draw a line tangent to the curve at the given time. Now that I have drawn a line tangent to the curve at that given time, I now can calculate my slope, which my slope you can think of it in different ways. Rise over run. You can say your change in y over your change in x. Some people like to even say y2 minus y1 over x2 minus x1. Whichever one you want to say doesn't matter, okay? As long as you're doing the change, the rise over run, you're finding your slope. Your slope of that line is equal to the instantaneous rate. Now let's reiterate this whole negative and positive business. What do you notice about the slope of my reactants here? My slope of my reactants is a negative slope, right? Well, that reinforces the idea that my change in concentration over time is negative. If I were to take the line tangent to the curve for the react product here, then my slope will end up being a positive slope. Well, that's because I'm increasing the concentration of my products over time. So this is all how you do instantaneous reaction rate. All right. So now that we know about instantaneous reaction rate, let's look at relative reaction rates. So I want to figure out what relative reaction rate is first off. Now, the word relative, right? It's something that's similar to something else, has some sort of relationship. That sounds pretty evident, right? Well, what have we been working with when we're talking about relationships of things? Yes, you got it, stoichiometry. Like I said, embrace it. So what is the relationship between NO2, NO, and O2? We have a 2 to 2 to 1 relationship. This also goes back to that graph, how we were saying, well, why is O2's graph, the increase in concentration over time, half of that of NO's because of that 2 to 1 relationship. So now we're putting actual, rather than just talking about it conceptually, we're trying to figure out exact values of those reaction rates. So relative reaction rate is if I have the rate of one thing in a reaction and I want to find the rate of something else in that reaction. Now you can definitely set up stitches. You can definitely figure it out the best way you whatever works for you, basically. I like to set up proportions. So my proportion for this would be, I know that O2 to NO2 has a 1 to 2 relationship. What that means is that the NO's rate, even though it is decreasing, right? It's decreasing, but it's going to be twice that of O2. So basically, in order to set those equal to each other, I know that I have the rate of O2 over 1, because that's my coefficient there, is equal to the rate of NO2 over 2. You see, I'm just setting up my proportion according to those coefficients there. Now, there's one thing that I'm missing. You see how this is a reactant, so that's a negative rate of NO2 that's there. So what do? Well, all I have to do is take this rate of O2 and say that that's 2.5. And then I just work with the math. So 2.5 times 2 is equal to 5. 5 is equal to the negative rate of NO2. So what would equal the rate of NO2? It would be negative 5.0 molarity over seconds, right? Molarity over seconds, that's the units for rate because it's changing concentration over time. And that is equal to my rate of NO2. So when you're working with relative rates, when you want to find the rate of something, when you know the rate of something else, all you have to do is set up a proportion by stoichiometry, figuring out what the relationship is between those things. So we've just gone through Maxwell-Boltzmann and how it relates to kinetics. We've talked about two types of reaction rates, which is instantaneous reaction rate and relative reaction rate. We have a few more types of reaction rates that we're going to do in a couple of other videos. So I hope this is helpful. I'll see you in class.